So, don't admit to any crimes, please. But yeah, other than that, I think we're about ready to go. Does anybody have any questions to start off the review? Okay. Well,
Oh,
if nobody has anything in particular that they want to start with, I'm just going to go down the list. I'm going to go ahead and share my screen. Can you all see? Let's see. Somebody please let me know. Okay. Thank you as always. So here's the um, list of topics that you must have for the exam. So the exam is going to be like 30 multiple choice questions and then one or two FRQ questions. And I'm pretty confident in saying, like, I've looked over the exam. I'm pretty confident that if you have all of these topics nailed, you should feel good about everything on the exam. There's nothing really that's outside of this scope. The topics for today are pointers, arithmetic. This was like week one. Stacks and queues, y'all just did this. Searching, and then the different types of sorting, and then of course big overview. Today I'm going to take a look at some of these slides briefly. I've prepared examples for pointers, which I just want to go over very quickly. I have some practice questions for sorting algorithms that we're going to go through, and then I want to really nail down big overview. I think that's what we're going to spend most of the time doing today, because most of the questions on the exam involve time complexity in some extent. So first thing on this playlist is a review of arithmetic with iterators and pointers. So I'm not going to go over all of these slides. If you want to go back over these later, go for it. But I am going to show you a little bit of code. So specifically, the point that I just wanted to make before we kick things off is that these two notations are exactly the same. And that has tripped up some people in the past. Like, I've looked at quiz statistics to see what are common questions that are missed. And essentially all that this program is doing include IOStream, namespace std, main function, return zero, like all your basic stuff. I declare an array, and then I declare a pointer to the second element of that array. So as it stands right now, pointer should point to 6. And the point that I'm trying to prove, maybe obnoxiously so, is that this is equivalent to this. So whenever you see a postfix increment that is attached to a pointer, whether it is or is not inside parentheses, it will do the same thing. And it's the same way with prefix increment too. So if you have a pointer and you prefix increment that pointer and then you dereference it, that is exactly the same thing as if you had done so inside parentheses. So if we compile this, hopefully we should see for this one 2 6s and for this one 2 9s, hopefully, right? So also quick note, if you haven't figured out how to compile a program yet, please do that now, because there is an FRQ on the exam, and the FRQ on the exam is going to come with like a testing suite, kind of similar to the way that the PAs come with a testing suite. And when there's 150 kids trying to submit their free response to the autograder all at the same time, it might crash, it might be slow, it might be buggy. So you can't rely on using Gradescope to test your code for you. You really have to understand how to run a test locally. I'm not saying that to scare you. I want you to be prepared, is my point. So to compile this code, you specify the name of the compiler, the version of the language, and then I called it pointers.cpp. As soon as I do that, it generates the a.out file. This should be review for most of you. And then, like we were expecting, 2 6s and 2 9s. So this notation is equivalent to this notation, and this notation is equivalent to this notation. I just thought that I would rehash that one more time, because there will be questions like this on the exam. Professor Lake is very fond of pointer arithmetic, so definitely go review some examples, but don't get freaked out when you see this. Okay, let's see. So that pretty much does it for pointer arithmetic. I just wanted to speed through that. The next thing we're going to talk about is the stack and queue abstract data type. So one thing to know about the stack and the queue is that it's a way of modeling your problem by using a data type that is suited to the problem. So whereas, you'll have algorithms that are suited to problems, you also have data structures that are suited to problems. So if you needed to model, for instance, something that was like a stack of lunch trays on top of each other, obvious hint, I said stack, right? You would use a stack to implement that. Whereas if you were trying to model the way that like people stand in line or the way that cars go through a stoplight, like those are instances of where you'd want to use a queue. So for the stack, you have very efficient operations for push, pop, and top. In fact, this is the only thing you can do with the stack. You can push, you can pop, and you can, like, sometimes this is called peek. I think peek is probably a better name for it. You can just view the top element without removing it. It's last in, first out. So basically, if you want to get whatever was pushed in, like what's at the bottom of the stack, you have to remove everything that's on top of it. Here's a stack example made by a person with a wonderful sense of humor. So you can see Mr. White here driving this truck. Essentially, as we, I'm covering it up. Essentially, as we follow this list right here on the right, you're going to see that updating the stack right here. So the first thing we do is we push 5, and then we push 9. See, it's taking a minute to load. Yeah, and then we push 9, and then we pop, so that would be removing 9, and then we push 23, and 23 will show up on the stack, and then we pop 23, and then we push 45, push 7, push 11. And I will warn you, as far as like test questions go, this is totally fair game. Like, even if you didn't have this little diagram right here visualizing what was happening, a common test question that I've seen is like, given a list of stack or queue operations, do some kind of calculation about the state of the stack by the end of the operations. So for instance, if it gave you a list of pushes and pops, like what will be the top element after they've all finished, right? And to solve a question like that, you need to count how many pushes happen and how many pops happen. So if you're here, we got 1, 2, 3, 4, 5, 6 pushes, I think, and then 1, 2, 3, 4 pops. So at the end, the top of the stack should be this 9, right? Because we've pushed 6 things and removed 4, I think. Maybe it doesn't always work out like that, but let's go ahead and oh no, maybe it's this 45. Okay, so point being, I just messed up. So be very careful when you're doing these problems. I recommend you actually have like notebook paper or something so that you can actually like diagram these things one at a time. I was just unable to do it in my head. If I can't do it in my head, I imagine somebody else will struggle to do it with that in their head. So anyways, the queue data structure is another very similar implementation to a stack, except for it's kind of like the opposite. So with a stack, you push and you pop from the top, whereas a queue, you push to the back and you pop from the top, just like the way that a line works in real life. So NQ or push is O of 1, DQ or pop is O of 1, and then front, view, peak, whatever you want to call it, is O of 1. And let's see, so we got another wonderful themed example right here. As you can see, the front starts at the beginning of the data structure, and we push 5 and we push 9. So as we're pushing to the back. Here we don't have a pointer that says back, but we are pushing to the back. Push 24, it's going to push something right here. Push 23 is going to be adding to the back of the queue, and so on and so forth. So you might see a question, given this list of queue operations, what is the final state of the queue? So be comfortable with that. And then as you can see, as we're popping from a queue, we're actually incrementing this front pointer. So it's like if this was a line of people that were waiting, you can see that as people come in, they have to wait in the back of the line. And then as the line is processed, like the front moves up. So, that's fair game. As far as amortized analysis for the queue, and I guess also the stack, the worst case that you could have for pushing, or in this case, when you're working with a queue, the push is called in queue, but it's basically a push. Worst case, if you are pushing on a queue that is implemented based on an array is you have to resize the array to have room for your elements. And in that case, obviously the time complexity is O of n, because you have n elements and you have to copy each of them. So that's one copy per element, hence O of n. I guess the best case would be if you already have enough space, and then it's just O of 1. For enqueuing specifically, on average, it's still constant time. I'm going to do this proof later today. So if you want to see somebody do the amortized analysis proof, you're in the right spot. I'm not going to do it now though. Okay, circular queue. Let's see. I did want to mention that the DQ is never going to take O of n time. So there's no reason whatsoever that you would need to resize your queue if you're popping. So I just thought that would be maybe important. Okay, so here's an example of a circular queue. And the difference between a circular queue and a non-circular queue is the way that space can be reused essentially in a circular queue. So as in the previous example, as we popped and moved to the front of the queue forward, we're leaving all of this empty space that could be utilized if you were going to use a circular queue. So specifically here, we push 3, we push 9, we pop, we push 4, and you're going to see what happens is we push where this back pointer is, and we pop where this front pointer is. And these things can move around the array. They're actually calculated by like a modulus operation. So as you can see, we push where the back pointer is. So back is 3 and we push here. You can see we push where the back pointer is. Pop is going to move the front pointer forward. So if we pop 3, the front pointer is going to come forward a little bit. So we continue to push and pop. You can see that push moves back and then pop moves front. And then we push 5, 12, 83. And as you can see, we got one more push, which now is going to move back to 0 and utilize this extra space that with a non-circular implementation was wasted before. And then you got 2 pops, and I think front should end at 4. So yeah, a kind of question that I can foresee in your future potentially is like, given this list, tell me, where does the back pointer end? Where does the front pointer end? So bring paper with you. Circular queue, worst case amortized analysis. So unlike with stack and queue, if a stack and queue is implemented on an array and you have to resize that array, that's when you do the amortized analysis. With the circular queue, there's no mechanism to resize, or at least not in this implementation. So the worst case will be constant time, the best case will be constant time, so on and so forth. Okay. So I think that does it for the stack and the queue. Yeah, I think that just about does. Does anybody have like any pressing questions that our wonderful PT has not been able to answer yet? Okay, she's on top of it, right on. Let's see. So next topic is going to be searching algorithms. So I'm not going to spend too much time here, because I did review these. I think it's the week 2 weekend review. You can find the YouTube video if you are so inclined. I'm just going to go over this briefly. So searching algorithms, the most naive searching algorithm is the linear search. Essentially just look at everything. So if you're searching for a maximum potentially, and you have a list of randomly ordered numbers, a linear search would be O of n time, because you have to check every possible entry within that list. In a linear search, the best case is if you're looking for something specific. Say I'm looking for, in this case, 112. Best case is you find it immediately. The worst case is you find it at the end, and then the average case is you find it somewhere in the middle. Still time complexity of O of n. If you know that your input is sorted, so super important that you know that it's already sorted, you can decrease your time complexity from linear time to logarithmic time using binary search. So essentially the strategy here is that if you make a guess as to where your target is, so say your target is like, I don't know, 92, you would first guess that it's somewhere in the middle of the list, let's say 23. If you know that 23 is less than your target, everything that's less than 23 is also less than your target. So never again will you ever have to look in this half of the list. And then basically you just keep calling that until you either find what you're looking for or you don't find what you're looking for. So specifically the worst case for binary search would be the case in which your target exists in a bad spot. So a bad spot would be like here. So that way you would just have to split, log of n times before you find your element, or it's not in the list. So I should have mentioned that before. When it comes to worst case for searching, if your target doesn't exist in the input array, then that's going to be also worst case, because you have to prove that it doesn't exist. You have to go all the way through the list. Best case depends. If your target just happened to be in the middle of the list, like if you just happened to be looking for 23 and you got it on the first guess, good for you, constant time. But on average, it's going to be log of n time. I'm not going to go over the implementation. We can review week 2 if you want to see. I actually coded this. Thank you. Okay, sorting algorithms. So y'all have seen this in PA2. Wouldn't be a bad idea to, get PA2 finished in the next couple days. I think the due date is coming up, relatively soon. I think it's Wednesday. Don't quote me on that. Anyway, so for bubble sort, this is skeleton code for bubble sort. Y'all probably know exactly what it does, so I'm not gonna describe the theory here. But what you will need to know for the test is that the worst and average case is O of n squared, which is where you have to do O of n comparisons n times. That's n times n, hence the n squared. The best case for bubble sort is going to be when you run bubble sort on an already sorted array. So you can see in this implementation right here, we've got a Boolean called flag, where if there are no swaps, then flag remains true. And no, flag remains false, and we break early. So bubble sort can recognize a sorted array and then end faster. And that case is O of n, because you still have to do O of n comparisons to make sure that everything is in the right spot, and then you can just return from there. So out of the naive 3, bubble sort, selection sort, insertion sort, bubble sort can recognize a sorted input, and so can see, which one is it? So can insertion sort. Well, I say recognize a sorted input, but essentially the way that they achieve the best case O of n is kind of different. So out of the 3, selection sort is the worst because it is always n squared, whereas bubble sort will recognize that you did no swaps and end your runtime in O of n, whereas for insertion sort, specifically, you would also be doing one comparison per iteration and then n iteration, so it's kind of like the opposite. But yeah, so insertion sort is usually n squared, could potentially be O of n. Selection sort is O of n squared even with the sorted input. The logic behind that is you're picking the minimum element n times, and even if the minimums are all right next to each other, you still have no way of knowing that. So specifically, it's going to be n times n minus 1 over 2. That's like the specific runtime. I did this example 2 weeks ago, so I'm going to skip this. I'm going to actually come back to my own example here in a second. And then the lower bound theorem. This is kind of tricky. The way that you word this answer could be right or wrong depending on very minute details, but essentially, the lower bound theorem is just a statement that if you're using a comparison-based sorting algorithm, the most efficient that you will ever be in your worst case is O of n log n. So the way that it's worded here is for comparison-based sorting algorithms, the worst case cannot be better than O of n log n. Just know that if you're using comparisons, the worst case will never fall below n log n. There are times where using comparison-based sorts, the best case will be below n log n. So don't get tripped up on that. If you see a test question that has lower bound theorem implied or mentioned in it, please take a second and read it in great detail. Because if they're asking you, is it possible for a comparison-based sorting algorithm to be less than n log n? It is. It is possible to sort a list in less than n log n with comparisons if the list is conveniently already sorted, right? So bubble sort would be an example of it potentially could break and log in, but it can't do that every time, which is what the lower bound theorem is stating. So we're going to get to non-comparison based sorting algorithms here in a second. Let's see. So I have prepared some examples. There are a few test questions that are going to look something like this. I mean, it's, you know, relatively probably pretty solid skill to have. But anyways, so let's look at this. We got sort number one. What sorting algorithm do you think would produce an output such as this? And please unmute yourself if you figured it out. Nobody, no takers. Let's see any patterns that you see in this input. Okay, well, if y'all are shy, that's fine. This right here is an example of bubble sort. One of the dead giveaways that you're looking at bubble sort is that one of the things that bubble sort does is that at each iteration, it finds the maximum element for that iteration, and you can see that progressively start to grow here. So this is the input. Nothing special happens on this line. And then as we can see, looks like the maximum has bubbled up to the end of the array. We can see the penultimate maximum has bubbled up to the penultimate position, and then so on and so forth. At each iteration, you can see, look, this subarray is growing and it's staying sorted here, which is an indication that we're looking at bubble sort. So that's bubble sort. Sorry that these numbers are out of order. It's crazy. But let's see. So for this next one, I'll give you all a second to look at this, try to decide what sorting algorithm was used in this instance. And I guess nobody wants to unmute, so I'm just going to go ahead and give the answer. This is insertion sort. One way that you know that it's insertion sort is, again, this is like the input to the array, so nothing fancy happens on this line. But as you can see, the sub-array, like the sorted sub-array, is growing each time. So in this spot, this is the sorted sub-array, this is the sorted sub-array, here, 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 and let's see, here, here. And one of the ways that you can tell that you're looking at insertion sort and not selection sort, because they are very similar, they both start sorting from the left, is you can see this minimum element right here doesn't move to the front until the last iteration, which is a giveaway that you're not looking at selection sort. Because if you were looking at selection sort, it would have found the minimum and then put it at the beginning, which is not what's happening. And then, yeah, as you can see, you've got 1 and then 9, and then you compare 2 and 9 and you swap it and put it in its place, and so on and so forth. Sorting algorithm number 3. Give y'all, I'm gonna renumber this. What was I thinking? Okay, so number 3, I'm just gonna tell y'all this is also bubble sort. So different input array, but as you can see, you've got the maximum element bubbling to the top each time. So 9 bubbles to the top and then 8 bubbles to the top. I guess it was kind of already in the right place. 7, 6, and then boom, it's sorted. So when we were saying before that, like, potentially you could be sorting an array faster or slower depending on best case, average case, worst case. This is an example where depending on, like, because number 1 was bubble sort also, depending on how you get the array, it might be either slower or faster to sort it. So this one is just slightly faster. I'm so sorry. I'm so sorry. I just cut out. Are we all still good? Let's see. Yes, okay. Apologies, y'all. I come to A&M. I use the campus Wi-Fi to prevent this from happening. Anyways, so this is selection sort. Again, selection sort is like a dead giveaway that you see the minimum appearing right at the beginning, and then the second minimum, third minimum appearing. Sort number 5, this is another instance of insertion sort. So maybe come back to this, convince yourself, and then another selection sort. Selection sort is probably the easiest to identify. So you're going to see a few problems like that on the test. Thought I'd prepare you. Okay, which brings us on to non-comparison sort algorithms. So non-comparison sort algorithms, I'm not going to spend too much time here.
Doctora, ¿cómo la
Go over the main points, basically. If you want to
No,
see a more
ocupadísimo,
in-depth
haciendo como cuál fue
view
al
of
mismo tiempo.
non-comparison sorting
Al mismo
algorithms,
tiempo,
please look at, I think, week 3, the week 3 review that I did, because I went over it in pretty great detail there. So you got bucket sort is, oh, and by the way, so these are all non-comparison based sorting algorithms. I mean, bucket sort kind of uses comparisons, but because they're non-comparison based, the lower bound theorem doesn't apply to them. And hypothetically, they could sort a list in
ya
linear
está
time.
en cualquier, donde ya se le dé la gana, ya está.
See. So yeah, sorry, I thought someone was talking. Essentially for bucket sort, the strategy here is just you bin all of the possible entries to a certain like predefined range of values. So for instance, you would sort 87 by putting it in this bucket, 34 goes in this bucket, 91 goes in this bucket. And then after having done that to each entry, you've got a pretty good idea of like an almost sorted list, and then you can run a less efficient sort on a smaller list right here and then put everything together. Boom. Just as a note, insertion sort is usually the one that's used to sort these little leftover arrays that are not sorted yet, because insertion is the best out of the 3. Okay, counting sort. You basically, in this example for counting sort, it's an algorithm that makes a sacrifice when it comes to space complexity. And in exchange for having extra space, you have a faster runtime. So you need 2 auxiliary arrays to run counting sort. One of them will store how many times you've seen each possible element, and then another one will show you the minimum possible position for each element. Again, look at week 3 review if you want to see me talk about this in great detail. This is also linear time, and let's see, this is like an animation of it happening. So your first auxiliary array needs space for every possible value. So in this world right here, every possible value is integers from 0 to 8. So we need to keep track of every possible instance of 0, every possible instance of 1, so on and so forth, all the way through 8. And as you can see, we counted 2 8s denoted by this 2 here. And right away, you can tell that counting sort might be inefficient if we were sorting really big numbers, right? Like if we had to, keep track of how many times have we seen, 42, how many times have we seen 1,000, right? Suddenly it starts, you can see that it scales to have just a crazy amount of space that you would need to be keeping track of. So specifically, yeah, counting sort works well with digits, but if you were like, I don't know, so sorting like phone numbers or social security numbers, there's so many possible combinations that this auxiliary array would be way too big to make that efficient. But anyways, as soon as you've counted how many instances you've seen of each element, you perform a rolling sum to give you the index of where you would start to see these elements. So see, rolling sum goes here. And sorry if I'm blowing through this. If you don't get it, it's because I've already done this for people who have showed up to the Sunday reviews. You can find my explanation there. If you're confused, I'm so sorry. But yeah, so that's basically the idea here. And then as soon as you've performed the rolling sum, 7 will be the index that you start to see 8s. So this array right here is 1 indexed, and to go from a 1 to a 0 index, you have to subtract 1, blah, blah, blah. So I encourage y'all to look through these examples and convince yourself. I just am not going to go over it today. Radix sort is like an upgrade of counting sort because it's actually efficient when it comes to large numbers. So essentially you can perform counting sort on each digit of a large number, 1 digit at a time, until everything is sorted. So you can perform counting sort on the ones place, and as you can see, that would look like this. So now all of these numbers are sorted by ones place, and then you can perform the same thing on the tens place, and so on and so forth. one huge note, one really important thing to keep track of here is that if you are performing radix sort, the way that you sort these digits must be stable. So as a refresher, as far as like terminology and vocab goes, the stability of a sorting algorithm refers to how it handles elements that have the same value. Like, does it preserve the order that they showed up in? So for instance, if you were sorting a list and that list was like 1, 2, 2, 3, a stable sorting algorithm would guarantee that two twos that you saw back to back stayed in the same order that they were when you sorted it. An unstable sorting algorithm might mess that up. An example of why you might need a stable sorting algorithm is radix sort, because specifically when you have sorted everything by the ones place, you never go back and sort by ones place again. So the reason you need stability is so that at each instance where you can see it's determined pretty clearly. When you have, like, for instance, 0 in the tens place, 0 in the tens place, 0 in the tens place, when you're looking at the tens place, like, you've already passed the ones place. So now that you're looking at elements that have the same tens place, the stability from the last sort that you did is super important here, right? Because you're never going to sort, like, if you have all of these zeros places that have different tens places, you're never going to see that. You're never going to see that ones place again. So it's important that the 0 that was here stays here, the 3 that was here stays here, the 9 that was here stays here. And then as you can see for these ones right here, actually that's a bad example, but let's go ahead and perform it on the hundreds place. And as you can see, stability is super important because look at all of these elements that have 0 and the 100s place. It's important that the 9, 12, 35, 56, 63, 73, 90 that were already sorted from the last iteration stay in order, because we're not going to go back and resort each entry that has the identical 0 in the hundreds place. So kind of a confusing concept to wrap your head around. If I didn't explain it well enough, please convince yourself that this is the case. And I think that's about it for non-comparison based sorting. Okay, so as far as the exam review goes, the only thing that we've got left, oh, and know how to compile locally. I cannot say that enough times. Let's see. So as far as what we're going over today, we're going to go over big overview. So I think Nihar's slides in here is a good video. It's a good slideshow. Maybe give it a look if you're interested. But I went over that the first week, so we will be going over this document instead. So I don't know if y'all have seen this. It was linked as like a additional resource material under week 4, but it's really good. This document is really good. And again, I'm gonna warn y'all, for those of you who are interested on what type of problems are showing up on the test, being able to analyze time complexity is like the most important skill that you can get from this class. And because of that, it is the like most prominent test question that you're gonna see. So specifically, this document right here starts off with a little bit of a little note of what does and does not count for runtime. So this is kind of shaky, and different people calculate this different ways. Particularly, what I need to mention is that the logic that operates a for loop or a while loop does not count. So if you've got a for loop and you're, declaring I equals something and then I plus plus, that logic, like the arithmetic that it does to increment I, does not count for our purpose. Also, what does count would be any type of operation and then any type of assignment. So specifically, this lists the operations that we're counting. So basic arithmetic operations, we got Boolean operations, and please note that these are not the one, like, I'm not including the ones that you see in the for loop and the while loop here. And then you got, any kind of like stream operations, so cin or cout. Okay, so let's go through these easy problems. So an easy problem asking you for a runtime would be like, read in a string of user input n characters long. Well, you have to read n characters, so n reads would be then pretty easy. Compare the equality of two strings of length n and m. So in this example, it would be you have to iterate through each character of n or m, and then you stop when you've reached the end of whichever one is the shortest. So this would be O of the minimum of n or m, but because they're both linear lengths, I would just say that this is a linear runtime, so O of n or O of m depending. Compute the dot product of two arrays, each of length n. So this is kind of unfair. If y'all haven't taken linear algebra yet, I don't expect y'all to know how to do this kind of thing. So unfair question, but a dot product of two arrays is essentially you just multiply each index of each array and then you add all those together. So if you have like arrays, in this case, like A and B, it would be A0 times B0 plus A1 times B1. And essentially that's going to be one operation per element. So that'll be linear time as well. And let's see, we've got the answer key here. I'm just going to go ahead and check as we go. So for the easy ones, yeah. So reading a string is O of n. As you can see, the second one was minimum of n or m, which in this case, we can just assume that is linear time. Computing the dot product is also O of n. Kind of unfair question for this class, but whatever. An n by m array is populated with random integers. Return the largest integer. Consider these math integers with no maximum value. This is kind of just a red herring right here. Okay, so an n by m array is a two-dimensional array. So to find the maximum element from the two-dimensional array, we're going to have to iterate through two dimensions, which is n squared, or in this case, O of n times m. There is no faster way to do that, I don't think. I do not think that there is a faster way to do that. So let's see what it says. And yeah, n times m looks good. Now we start getting little pieces of pseudocode here. So for instance, we've got a function that they say, like, take my word for it, it's O of m cubed. So the function magic has time complexity m cubed. If we look at this code right here, Apple runs n times and it runs m cubed n times. So therefore the runtime here would be O of n times m cubed, which yeah, should be here. And I'm sorry if I'm going too fast. This is the easy section. I'm gonna take more time in the difficult section. And then let's see. So we've got a while loop right here. So while n is greater than 0, n divide equal by 2. So this will be log time. This is just the definition of log time. And then last but not least, while n is greater than 0, n divide equal by 3. And that should just be log base 3. Yeah. Okay. So now, deep breath. Made it past the easies. We're going to actually think about these mediums. So in this example right here, we've got O of m cubed time complexity and this function called magic. And we just need to like take their word for it. Let's see. So banana runs magic. So we've run m cubed once. And then I don't think we ever call this function again. And we run a loop from 0 to n. So the time complexity here, you would have to pick between which is worse. Is it worse to run this function for m cubed, or is it worse to do this this loop for O of n time? Technically, the runtime would be like m cubed plus 2n. But I think for this, we can probably safely assume that quadratic runtime is worse. So I'm going to say this is like O of n squared or m squared. Let's see, what does it say? Yeah, so technically it's big O of m cubed plus n, but you can pretty much assume, you can pretty much make this assumption right here that m cubed is worse than n. Okay, that one's a little bit tricky. It's heating up a little bit. Okay, so now we've got same function magic that has, take my word for it, m cubed runtime, and then we've got this function O of m magic 2, which takes just linear runtime. And for n iterations, we decide between running the first one and the second one. Now this is tricky. This is tricky because when y'all have seen conditionals in runtime before, you've been taught that you need to evaluate the worst possible case scenario. So in this case, we either we're picking between running this cubic function magic one time or magic 2 n times. So we're going to run one call to O of m cubed and then n calls to O of m. So technically, the time complexity for this function right here is going to be O of m cubed plus m times n. And we don't really know which one is worse, right? That hasn't been specified. Like we don't know the size of n and we don't know the size of m. So to answer this question, whenever you see a conditional, the runtime or time complexity for that conditional is the worst possible scenario that you can think of. And in this case, we don't really know which one is worse. So I think the best answer would be to write both of them. And as you can see in this solution right here, it's pretty much just says the same thing. So it's O of m cubed plus n times m. We don't really know which one is worse. We can kind of assume that cubic time is worse than n times m, but again, we don't really know. Let's see, for this function right here, find the runtime of cherry in terms of n and m. So looks like we're looping from I is equal to 0. We're multiplying n by 2 at every iteration. And then let's see, if C, I don't know what this operation does, probably some kind of logical thing, but basically it's an if-else condition, and then both of them are linear time. This one is maybe an example where you'd have to like squint your eyes and look really, really closely, because this one is a trick question. I think this is a trick question, because as you can see, we've got int I is equal to 0, I is less than n, I times equals 2. If y'all finished PA1, the vector PA, and you remember having to add that weird edge case for the grow function, this is essentially what's happening there. You're trying to double 0 for forever. And I don't think this function will ever finish. I think this will just run forever. So should be like O of never stopping, O of infinity. Yeah, so be really careful, because I try to be like a cool TA and make this class like a learning environment. Some of them are out to get you. Like some of the people writing test questions just want to like, they don't want to test whether or not you know the material. They want to test how closely you read the problem. So please read the problems very closely, because your grade will depend on it. Okay, so let's see. I'm going to spend even more time on this next section. We got the hard problems. So compare equality of n strings. So it looks like that's the number of strings that we're comparing, each of length n underscore I. So I assume that each string is a different length. And then return true if any pair of strings matches. Let m represent the largest input and m prime represent the shortest input. Okay, so for big O analysis, we're looking at the worst possible runtime that we can think of. And immediately, my instinct is to think that the worst case would be if we never found a comparison that was true. So if all of the strings are different, then we have to compare n strings to n other strings. So you could think of that as like, there are n squared possible combinations of comparisons, and then each comparison is going to be also O of m. So this should be cubic time, I think. Let's see what it says. Yeah, pretty much what I just said. So it'll be n times n minus 1 over 2 possible ways to compare different strings. And should be that should happen m times. So basically cubic time. Let's see, next one, an n by m array is populated with random integers. Each row is in sorted order. Return the largest integer. So for this one, we can leverage the fact that we know that the each row, and this is like a 2D array. We know that the maximum element from each row is going to be at the end of the array. So we can just look down the last column, right? And the last column will have all of the maximum elements. So like we can be guaranteed in a problem like this that we're never going to see a maximum element that isn't also the maximum of its row, right? If it's the maximum of the entire two-dimensional structure, it'll be also at the end of its row. So we can just check a column and that'll be O of n time. Yeah. Let's see, one last hard question we got here. Find the runtime of this nested loop in terms of n. So this one is really tough. This one I had to like really sit and scratch my head on. So as you can see on the outer for loop, we've got I is equal to 1, I is less than n, I plus plus. And then in the inner loop, we've got j is equal to I, j is less than n, j plus plus. And then the operation that we're doing here is n divided equal I plus j. So specifically, what we need to watch out for in a question like this is we're modifying the upper bound of our loop. So as you can see, if n is an input, say n is maybe 10, n is going to be changed as we run this loop. So we're not actually looping from 0 to 10, I mean from 1 to 10, we're looping from 1 to wherever n will be by the end of that loop. If you do some like mental math, you can see on the first iteration, I will be 1 and then j will be 1. So the first iteration, n will be divided equal by 2, so n will be 5. The second iteration, I will be 1 and j will be 2, so now you're dividing equal by 3. And the formula for a loop where you divide equal the upper bound is logarithmic time. So this is slightly more efficient than logarithmic time, but you can say log time as the O of n upper bound. This one is really tough because you've got 2 for loops and it's log time. Let me just confirm. Yes, this is logarithmic time right here. Super confusing. I don't think that you're going to see a question that's quite this hard, but anyways, we made it past those. And then let's see, the last thing we've got is intense level problems. Let's see. So amortized analysis. Show that expanding a vector by doubling has O of 1 runtime. Assume n inputs. So earlier in the review, when I blew past saying that, pushing to a stack or a queue that has array implementation, when I said that it's constant time on average, take my word for it. This right here is the proof. I'm just going to show you the proof and kind of like intuitively walk through it. So this is what it would look like to double the array that you're pushing to, right? So if the array has 1 element, you don't have to double, but then you double it 2, you double it 3, you double it 5, and you double it 9. So essentially, as you continue adding things to the array, you're looking at a sum that looks like 1 plus 2 plus 4 plus 8 plus 16, and so on and so forth. And to find the average runtime of this operation, the average is going to equal to the total runtime divided by the number of times that you run the function, right? Does that make sense to everyone? Like average is equal to total total divided by number of occurrences. So the total number of operations, as you can see here, would be 8 plus 4 plus 2 plus 1, which, as you can see, will be roughly 2n. And then the number of times that you would call this in this instance would be n. So an amortized analysis would be saying roughly on average, the insert, or not the insert, but the resize for each insert or pushback or queue, however they phrase it, would be roughly 2n over n. So roughly 2, so constant time. It's kind of a mouthful. I think you will probably see a test question like this. So just go back and prove this to yourself if you don't understand it. Don't get caught up in this fancy math here. I know it's kind of a lot to take in all at once. If you're interested on how this gives you 2n. You can look up, I think it's called Zeno's paradox. It's kind of interesting. But again, don't be scared. Just get it to where you understand it conceptually. And then let's see, last one. You're designing an algorithm that will take an input as an n by m matrix and return the largest number. Design an algorithm to do this and better than nm, or justify why there is no algorithm. This doesn't belong in the intense category. This is easy. There is no algorithm. You basically just have to search. It's like a linear search twice. Yeah. So don't trip about this one. It's kind of a bad question. Okay, so before I open it up for Q&A, like open Q&A, that we can start talking about things, I want to clear up one last confusion with runtime. And I kind of debated not doing this at the end of the review, but this is probably the most important thing that I'm going to say for the entire review. So if you've been daydreaming, wake up now, 5 minutes. This is super important. This is literally like 10 questions on the exam. It's just understanding what time complexity even means. So I just spewed about a bunch of nonsense about how you would classify the runtime given a bunch of different scenarios, but what does runtime mean, right? Runtime means asymptotic time complexity, asymptotic worst case time complexity. So breaking that down, as you can see here, I've got two functions. So imagine the y-axis is number of operations and the x-axis would be input. As you can see, a logarithmic time complexity should be lower than a linear time complexity, right? Like y'all remember seeing those charts that's like, like constant time, log time, linear log time, so on and so forth. That might not be true in the immediate short-term case. So it's possible that between these bounds, the linear algorithm actually might be efficient with a lower time complexity. So when we say time complexity, you cannot just assume that an asymptotically better algorithm will outperform an asymptotically worse algorithm on a smaller output. And this is kind of a visual proof of what that looks like. So for instance, if you've got like an efficient function with a high constant multiple versus an inefficient function with a low constant multiple, then you know that there's going to be some point at which those two functions intersect. So there will be some point at which one is better than the other, and then at some point that order will be flipped. So you might have to do like some calculations as to like, imagine you have an input of size 20. Is it better to pick the linear time or the logarithmic time? And in this instance, you can see on an input of size 20, it's definitely better to pick the linear time, so on and so forth. So y'all will see like a few questions like this. I think having this visual in your head is definitely super helpful. And then the last thing that I wanted to go over today is I put together this little proof. So another type of question that you're going to see come up a lot is, how does the efficiency of your algorithm scale with the size of your input? And I don't really think there's been much like coverage of this in the lecture. You kind of just have to like intuitively understand it, but I'm going to prove it to you. So here's a list of very simple proofs that I think will save you on like 5 or 6 questions probably on the exam. So for the purposes of this document, a of n is just some arbitrary function, and f of n just counts how many operations happen. As you can see, what happens to a linear function when we double the size of the input? Well, if we say that this linear function a of n takes f of n complexity to run, then a of 2n is going to take f of 2n complexity to run. And as you can see, we can factor out this 2, and then using this definition up here, we can do a substitution, and we can say that for a linear function, if we double the size of the input, we've doubled the amount of operations that need to happen. So pretty simple. I think that's straightforward. This property right here between line 2 and 3 is a property of linear functions. So if you've taken linear algebra, you know how I did that. Otherwise, don't freak out. Point that I'm trying to make is that linear functions scale with their size of their input. So what about quadratic functions? So if you've got some function, a of n has got quadratic runtime, what happens when the input doubles? Well, as you can see, when we define it in this way, when our input is of size 2n, then now we're running time complexity on size of 2n. Then we can split this exponent over 2 and also n. So now we've got 4n squared, factor out the 4, do the substitution like before, and this is a proof that when you have a quadratic function and you double the size of the input, you have now increased the amount of operations by fourfold instead of twofold. So again, pretty straightforward, and I am beating a dead horse with this third example, but I really want to nail it home. What happens to a cubic function when you double the size of the input? So specifically, if we've got some kind of cubic function like a of n is equal to f of n cubed, when we double the size of the input, we are now increasing the number of operations by eightfold. So, so on and so forth. Divide and conquer. Y'all should have this nailed down. The last example maybe is a little bit more tricky. So what happens to a logarithmic function when you double the size of the input? And this one right here, as you can see, so a of n is defined to be some function with logarithmic time. A of 2n is going to be some function with log of 2n time. As a property of log, when you have things multiplied inside a log, you can split them up like this. If you haven't seen this in math, don't worry about it. But essentially log base 2 of 2 is just 1. So now we've got f of 1 plus f of log of n. And that's a proof that when you double the size of the input to a logarithmic function, you are increasing the number of operations by 1. So hopefully that'll help you. I hope you woke up in the last 5 minutes, because that's super important, like probably the most important thing that I've said in the last hour. Like the combination of this and this, just understanding what they're actually testing you on. Okay, that being said, that should have y'all pretty well prepared. If there is something that I blew past that you're not comfortable with, I think everything that I mentioned is probably important to be successful. So there's something you're not comfortable with, please ask me now. I'm opening up the floor. So any questions? See, someone is asking for these documents. I'm gonna go ahead and paste the link into the chat one more time. Y'all go watch those videos. Like the TAs who made these materials put like some, very genuine effort into them. There's good stuff. Let's see. We got any other questions though?
Could you explain the difference between when runtime is n minus 1 over 2 versus n times n plus 1 over 2?
Yes. Yeah. I'm gonna go ahead and share my screen again. So y'all can see this still? So the time in which
Wait, it's I don't think it's showing. Okay, now it is.
Okay, so the case in which I think so for here, it was in one of these examples, wasn't it? I think. It was the hard example where, yeah. So essentially, when you're searching a grid like this, like as in you've got n possible strings and then n possible strings, there are n times n minus 1 over 2 possible combinations of those strings. So specifically, the reason that it looks like this is because this is, I think there's a name for it, but this is an arithmetic sum, essentially. So if you look at, like, if I were to Google just 1 plus 2 plus 3 plus 4, this would load. So the visual proof of what this looks like is it's still a two-dimensional space, but essentially you're doing 4 comparisons, then you're doing 3 comparisons, then you're doing 2 comparisons, then 1 comparison. And so, let's see, where is what I'm looking for? Okay, but I essentially you can think of this summation as like, if you do the outer for loop 4 times, and then now you do it 3 times, now you do it twice, now you do it once, right? For in the example before, we're comparing strings. So this is how many possible combinations exist at every iteration. The sum of these things is just defined to be this by definition. And then the n+1 or n-1 depends on whether or not you include the last iteration of this process. So see if I can find what I'm looking for. Man, nobody wants to help out. Let's see if I can. Yeah, let's see if this will. Man, nobody wants to show me, but okay. Essentially, you can just you can think of this as like a triangle of sorts, right? So you've got like a grid space that you're searching, and you're searching like 1 iteration, 2, 3, 4, 5, so on and so forth. The reason you would see that in computer science is whenever you've got a loop where it's like from I is equal to 0 to I is equal to n, and then j is equal to I, j is equal to n. So it'll be n, and then n-1, n-2, so on and so forth. So good question, just depends on where you stop the loop. Usually that's modeled when you're thinking about possible combinations in a search space, or also for specifically bubble sort has this time complexity. Because if you've guaranteed that you've like found the biggest element here, and then you've guaranteed you found the biggest 2 elements, biggest 3, biggest 4, you're now looking at kind of like a triangle of sorts, right? Because you, at first, you have to do this many comparisons, and then this many comparisons, and then this, and then this many comparisons. And same thing with insertion sort, like the sorted subarray will keep growing. So you've got to do like, comparisons, if that makes sense. When I say triangle, that's what I'm talking about. It's like kind of half of your search space. Does that answer your question though?
So like what if you have like a for loop that goes through from 0 to n-1 and a loop that goes from 1 to n? Both do n comparisons, correct? But one of them is like non-inclusive while the other is inclusive. So how would those two be different runtimes if they have the same iterations?
I would say if you're including whatever level it is, like in this example, if you're including like this level and saying like you have to do comparisons for it would be more accurate to say like this last level, or for bubble sort, like including this one, that'll just be the difference of like a minus or +1. And I'm sorry, I'm not prepared to like I don't have a way of writing equations. If I had like an iPad or something, I'd be happy to like actually diagram it, but send me an email and I'll send you like a photo of a proof or something.
Okay, all right, thank you.
Any other questions? I'll
I have a quick question.
Yes.
It might be hard to answer because you don't have an iPad, but it's like we're doing an amortized analysis, and instead of like multiplying by 2 every time to resize, we add 10. Can you like talk through what it would be?
Yes. So y'all have taken the PA1 demo, right? I think there was like a randomized test bank, so not everybody saw it. But I think one of the statistically most missed questions on the PA1 demo was like essentially exactly that. Like as in, what's the amortized analysis if you double the array each time versus what's the amortized analysis if you add 1 space each time? So, and those two like simple examples, if you're adding 1 space each time, then you have to copy everything and resize every single time that you add an element. So every time you have to add an element, you have to do n copies essentially. So that would be linear time complexity, whereas the amortized analysis is constant time complexity. In your specific example, if you are resizing every 10 inserts, then that's still O of n time complexity. That would be like let's see, that'd be like this essentially. So as you can see over time, like the asymptotic behavior of doubling is actually more efficient than adding 10 spaces every time. But at this critical point right here, you can see maybe you at the beginning get away with having it be a little bit faster if you're not doubling from like 1 to 2 to 4 to 8 and so on and so forth. But yeah, essentially if you were to perform amortized analysis in that way, it would be like n copies every 10 times. It would be like a function kind of like this. But good question though. Anybody else? Anything at all? You don't want to. Y'all know I've seen the answer key, right? Like, I mean, if everyone is shy, then that's fine. Okay. Well, I guess I'm gonna call it here. Thank you everybody who showed up. Can we ask questions about the homework? I'm gonna go ahead and stop recording, but yeah, why not?